Friends, Erlangers, Beamers, lend me your ear. I come here to bury the beam, not to praise it. I come here to speak at the beam's funeral. The beam was my friend. It was just to me. But the world says it was too ambitious. If it was so, it was a grievous fault. Nowadays, we have Rust, Node.js, Dockers, and Kubernetes. Why would we need technologies from the 80s for running on Solaris rack servers? No. I think it's time to bury the beam. But before we do, let me go back and talk a little bit about the history of the beam. And the history of the beam, of course, starts with the history of Erlang. As you might know, Erlang was developed by Ericsson in the 80s. And some foresight managers realized that Ericsson was spending more money on software than on hardware when they were building new telephone switches, and especially when maintaining telephone switches. So they decided to start a computer science lab within Ericsson. And it was almost exactly 40 years ago. It was March 1st, 1984, that this lab was formally started. In this lab, Erlang was developed to meet the demands of telecom systems, which requires to handle numerous tasks concurrently and reliably. Telecom systems, they have to provide high availability, meaning that they have to always be operational and have real-time capabilities to handle setups and teardowns of calls. Also, reliability is important, and they have to continue to run even if some hardware parts fall apart and stop working, or some software stop working. They should be reliable and continue working. Also, they must be scalable. And since the telecom industry is continuously growing and the number of telephone calls were increasing all the time. Nowadays, I don't know whether there's so much telephony anymore, but at that time, it was increasing all the time. Finally, it had to be maintainable because these switches that they built, they lasted for at least 30 years, standing sometimes in the wilderness. So you need to be able to maintain them and update them and repair them without any downtime. So to address this, Joe Armstrong, Mike Williams, and Robert Wirding, under the leadership of Bjarne Dekker, experimented with new languages. And they were focusing on concurrent processes that can operate independently with no shared memory. At this time, Ericsson had been developing telecom systems for some time already. And many of the ideas that later came into Erlang came from languages such as Plex and Erik Pascal. These languages already supported hot code updates and processes. Erik Pascal was a concurrent Pascal implementation created mainly by Bjarne Dekker. And the first experiments with this new language, we try to combine these ideas with new symbolic languages of the 80s, were first implemented in Strand and later in Prolog, and later it became the Jam. It was from Prolog that Erlang got most of its syntax. And the first virtual machine, the Jam, was heavily inspired by VAM, the prominent Prolog virtual machine. And even in the Beam today, we can see that it has X and Y registers, which is something coming from the VAM. In 1994, that's now 30 years ago, during the third year of my master's studies in computer science, I was introduced to Erlang for the first time. I had been programming since 1980, and I decided to study in Uppsala because they still, in 1992, when I went to the university, they still thought both Lisp and Prolog. And I believe that these languages would be really beneficial to kickstart my career as an adventure game programmer. And one of the reasons that I was interested in learning Lisp came from my first visit here in California. So in 1987, I came here as an exchange student. And as you might have guessed from my accent, English is not my mother tongue. Swedish is. So when I came here, I had to translate everything in my head before speaking. But after about 2 months, I started thinking in English, and this was great. Now I could speak much, much faster than before. I didn't have to translate back and forth. Unfortunately, after a few days, I realized, God damn, I'm stupid. Because suddenly, there were a lot of thoughts that I used to be able to think that I couldn't think anymore. Because my grasp of the language was not good enough. And this taught me a valuable lesson on the impact of language on the way that you think. And this also applies to programming languages. Fortunately, at the computer science in Uppsala, it was a great place to learn many programming languages because every course was taught in a new programming language. So I got to learn lots and lots of different programming languages there. And at some point, finally, Erlang also. Now I might admit that I lied in the title. When I started programming Erlang, the Beam had yet to be released. So it's not 30 years on the Beam, it's 30 years with Erlang, but almost 30 years on the Beam. And in the title, it also says mastering concurrency, and I have not yet mastered concurrency either. But anyway, just as I began to learn how to program Erlang, a new arrival at the CS lab, Bogomil Hausman, started on Turbo Erlang. That was an Erlang to C compiler, and the C code could then be compiled to native code. Unfortunately, it was tricky to handle tail recursion in C, and this was essential since Erlang doesn't have any loop constructs. So after a while, the C compiler path was discontinued, but the macro language that was used as an intermediate code step going to C could be interpreted, and thus Beam, Bogomil's Erlang abstract machine, was born. But it wasn't until 1998 that the Beam became the default interpreter instead of Jam. And the Jam and the Beam coexisted in the same source code for a long time. What we call the Erlang runtime system. Today, when we talk about the Beam, we usually mean the entire runtime system, not just the virtual machine. But some parts of this runtime system are still more or less the same as they were with the original Jam virtual machine. But let's go back to the telecom requirements, and that led to Erlang and the Beam. So the Beam has many features that help developers, such as dynamic typing, exceptions, and the right primitive data types, such as ports, atoms, arbitrary precision integers, lists, tuples. Other features such as hot code loading and the interactive REPL also helps. And we have Erlang OTP with excellent libraries like etstats, Mnesia, supervisors, and gen servers. Still, it is Beam's concurrency model that makes it easy to build available, reliable, scalable, and most importantly, maintainable systems. So let's look at some of the details of this concurrency model. Process isolation is a fundamental feature of the Beam. It serves as a foundation for all other features. Process isolation ensures that one process cannot access the memory of other processes directly. Additionally, if one process crashes or stops working, it should not affect any other processes directly. Joe Armstrong believed that process isolation is the most natural way to model the world. He argued that, for example, the people do not have direct access to other persons' memories and thoughts. In object-oriented languages, objects often have direct references to each other when modeling the world. As a result, the state of one object can change by actions in another object. The lack of process isolation is the root cause of the rising popularity of microservices. Here's a little thing for you to tweet about. You are often forced to model isolation with independent services running in a container to achieve true isolation between independent processes if you don't have the Beam. Now, we should differentiate between process memory being isolated and processes being able to communicate. The need to communicate takes us to the next concept, signals. Processes communicate with each other through signals, which enable them to exchange information. The most common used signal is the message, but we also have exit, link, unlink, monitor, and demonitor, which help us build reliable systems. Using these signals, we can create a robust system. For example, a link establishes a two-way connection between processes. So if one crashes, the link process can either crash or handle the error. On the other hand, monitor is a one-way signal that informs one process if another has terminated without affecting the monitoring process. With these, we can build supervisors and process hierarchies that let us restart processes when necessary. If we have time, I have a story about signals that we can get to in the end. Another important part of the Beam is the scheduler. There's always been a scheduler in the Beam. In the Jam and the early versions, there were only one scheduler. And each process will run for a short time, and then the scheduler will pick a new process to run. The time slot a process gets to run is determined by the number of reductions that the process is using. A reduction is a small amount of work. It's not defined exactly what, but small amount of work. Each function call consumes one reduction. And when a process has consumed the default number 4,000 reductions, it has to yield, and another process gets to run. In 2006, the first version of Beam with multi-core support was released. And this one has one scheduler per core. And finally, we had true parallelism in Erlang. And we could have 2 or even 4 processes running simultaneously, because that was about the hardware we could get. If we had a server with a quad CPUs, we could even get to 16 already at this time. But this increased quickly. If we have time at the end, I have a story about schedulers. One other important but often overlooked feature of Beam that makes it easy to build robust system is automatic memory management. Today, most developers expect that their programming language will provide some kind of memory management. But when Erlang was introduced, this was rare among the popular languages of the time. The process isolation we discussed earlier also helps to make memory management scalable. Since there are no references between processes, each process can be garbage collected independently. This leads to very short garbage collection times and no stop-the-world GC. With several schedulers, we can even have processes running at the same time as other processes are garbage collecting. During my time with the Hype group, we experimented with different hybrid and global heap solutions to avoid the copying of messages during message passing. At the time, we concluded that 1 heap per process was the best, because most messages were small. So the cost of copying between heaps was much less than the garbage collection cost. Since then, the garbage collector has been improved several times. And if you want to know more about garbage collection in Beam, there's a nice paper by Lucas Larsson, a Medium article that you can read. If you have time at the end, I have a story about garbage collection. So during my time at Klarna, we pushed the limit of Beam several times, which led to small but important improvements. As you have heard, I have several stories from this time, but unfortunately we don't have time for all of them, but let me tell you one now. We were performing hot code updates of our system almost daily, and this allowed us to have minimal downtime and very fast releases. But one day, the system fell over after an upgrade. It's not a big problem since we had a redundant system with several servers. But after this, the system started falling over more or less every second upgrade. And there were no traces in any logs. We started hunting this problem locally on a developer machine. By looking at the types of updates that caused the system to fail, we noticed that there were always included updates to our credit policy. At the time, the top level of the credit policy was implemented in a domain-specific language, implemented in Erlang and compiled to Beam code. This was a high-level backtracking language that the business people could use to write these policies with. This didn't really pinpoint the problem, but now we could reproduce the problem by updating the credit policy several times. When doing this on a development system, we finally got an output from the system. Beam catches cons, no free slot, sad face. So getting this sad face meant that we could search the Beam code, and we found a printout and an exit 1. And it turned out that when we started our live system, we managed to get standard error to dev null. Oops. But after fixing that, we could actually get this also on the live system. Nice. But having found this little piece of code, it was not that hard to look 10 lines above it and find should use dynamic relocation. So you could only have 16,384 catches in the whole system. And since we had a backtracking DSL that was implemented with catch and throw, we used a lot of catches. And with hot code loading, keeping 2 versions of every module, we had almost twice as many catches in the system after every second upgrade. And then, of course, the system crashed, and we had fewer catches again. So, problem solved. We fixed it locally, sent a patch to OTP. They threw it away and wrote their own. But nowadays, you can have 67 million catches on a 32-bit system, and I can't even calculate the number on a 64-bit system. So it takes years and years to find all these potential problems with a system of the size of Beam. Fortunately, we have had 30 years of continuous development of the Beam by the OTP team and by serious users of the system. And nowadays, when the Beam is open source, we can get contribution from the whole Beam community. While working on the Beam, I have not only been deep into the runtime system, C code, but I have also been thinking about how to build large-scale systems on it. So let us now turn to the question of how to design concurrent systems. After we have been discussing the reason behind Beam, its history, and how it works, we can start considering how it affects system design. So we should remember that processes are the most fundamental feature of the Beam, which provides encapsulation and abstraction. However, programming languages running on the Beam only partially reflect this. Processes aren't first-class objects in the language. We can't really talk about processes themselves. We can only those are first-class objects. We can create processes with spawn, but what we're spawning is actually code. So we typically focus on the code in a programming language and divide it into function, modules, and applications. These abstractions are orthogonal to the processes abstraction. When we create a module with a gen server behavior, it makes it easy to think that this is the module, is the gen server process. But in reality, the module is just some code that the process will execute. Other processes will even execute some of the callbacks in that module. I don't blame the designers of Erlang for this. They studied alternative programming methods such as Strand, Prolog, data flow languages, and actor-based paradigms. But they realized that pure sequential programming with processes was still the easiest way for programmers to grasp and reason about these kind of things. Nowadays, with the popularity of Kafka, we have seen a new wave of flow-based programming libraries such as Apache Flink, Apache Spark, and even Apache Beam. No relation as far as I know. We could also throw TensorFlow into the mix. I still agree with the designers of Erlang that sequential code executed by independent processes that communicate through message passing is the easiest way for humans to program complex systems. Still, we will need some mental tools to help us separate the abstractions in code from the abstractions in processes. In object-oriented programming, we organize code around classes that define objects which contain methods. Calling methods can often be referred to as sending messages. But there is also a close correspondence between a class, the code, and an object, the runtime incarnation of the class. On the other hand, in Erlang and Elixir, modules act as namespaces that group related functions. They do not specify whether or how processes execute the code. Any process can use any exported function from any module. In Beam, processes embody the actor model running concurrently and communicating through message passing. This architecture fosters system resilience as each process independently manages its state and recover from failures, enhancing robustness and reliability. But unlike object-oriented programming, which prioritizes data encapsulation and hierarchy, functional programming on the Beam emphasizes computation and transformations. It shifts the focus from manipulating data structures to defining functions that transform inputs to outputs. This functional approach facilitates reasoning about code and side effects management, which is critical for building these kind of systems. Unfortunately, still no Beam programming language helps you think in processes. So let us look at some of these tools for thinking about processes. I think that processes in a computer system can be compared to workers in an organization, with each process performing its own specific task. It is important to note that processes are not the code itself or the module where the code resides, and they cannot be compared to objects in object-oriented programming. Instead, each process is an independent actor that works in harmony with others to complete tasks efficiently. Think of processes as gnomes that reads the code in a module and executes the command written in the code. The code is simply a set of instructions, and it is not the process itself. The gnome, or the process, can have a state, which is the memory and thoughts in its head, but it can only communicate with other gnomes by speaking with them or sending messages. And multiple gnomes can read the same code and execute instructions in parallel. When you start to view your system in this way, you will find it easier to separate the code from the processes. Designing effective processes in Beam requires a shift in mindset from thinking about objects and modules to focusing on flows and tasks instead. Think of each process as a dynamic actor in a larger play with a clear execution flow. Consider the actions it will perform, their sequence, and where it will travel within the system. At the same time, consider the information flow and the messages that the process will exchange. This includes who will receive them and how this communication will orchestrate the overall system behavior. By emphasizing a flow and task-oriented design, we can clearly envision how processes interact and their respective responsibilities within our application. Consider processes as dedicated workers, each fully completing a specific task. When tasks are large, divide them into smaller, manageable units, aligning each to a single process. While a process might tackle several tasks, make sure it sees each one through from inception to conclusion to make the workflow of the system clearer. And focus on specific actions when you define the task for your processes. Examples of a task could be user authentication, placing an order. So each task is a distinct actionable process within the system. Another thing to avoid is overusing gen servers in your system design. A process does not have to be a gen server. While gen servers are beneficial for specific needs such as synchronous operation, gen server call, and serialization with handle call, remember that these features come at a performance cost. So use gen servers only when you need these kind of synchronizations. We can see a number of process archetypes for performing tasks. So thinking about these different types of workers is helpful. Some examples include pool workers, short-lived workers, and long-lived workers like gen servers, servers I also see as workers, handing over work to another worker, or as a manager. Other sets of processes controls the flow in the system. They can work as a point of synchronization or as a lock on a resource. They're also helpful in serializing the flow. A third type of processes handle data flow, such as the processes that listen to incoming ports or sockets, or keep track of a specific resource. And finally, we have processes such as supervisors and insulators that are used for error handling and recovery. I'm sure there are a lot of other types of processes, but starting to build up your mental picture of these different tasks will help you design your system. So when you're designing the processes, think about flows and tasks, but then when you think about your code, think about domains. And now I'm talking about domains of specific business domains. So for your code, divide it in domains like user domain, manage everything with the user profile, order domain, handling orders, and so on. And organize your code in domains. So now that we have looked at the history and a little bit about the design, and also took a detour on how to design concurrent system, let us revisit the question, do we need the beam today, or should we abandon it? Or are we perhaps on the verge of a new beam revolution? The beam was designed to address certain issues in software development, particularly the need for fault-tolerant, highly concurrent systems. These needs are still present, especially given modern software application growing complexity and scale. Abandoning the beam would mean discarding a proven, reliable system that offers strong isolation of different processes, high availability, and a powerful way to build a resilient system. And a system that has been incrementally and carefully developed by the OTP team and the community for over 30 years. As for a new beam revolution, the signs towards a renaissance rather than a decline. So there's a rise of technologies that require beams robustness and fault tolerance. Edge computing, containerization, Internet of Behavior, energy efficient computing. And I even know of some space projects now that are looking towards Erlang. I know that there are space projects that are writing their control software in Python, and then I think we have a better case. So I think the beam is more relevant than ever, but we must recognize and improve its weaknesses. When I started thinking about this presentation, I also thought about these weaknesses, and this led me to a new framework called ABBA for agent-based, beam-based architecture. Here we should try to find the things that need to be better, like the modularization. It's not so good that You can call any module, any exported function in any module. We need some type of orchestration of agents and a registry of services. I think better protocols for talking between systems. And I think message queues has been proven as a very nice technique, and I think we should have these as system boundaries. So process message queues really good locally, but having some message queue implementation where you can have broadcast and addressing at the edges would be good. So I've written a position paper that's available on GitHub. And yeah, if we can see how long time it has taken me to write a book, now I'm going to write a framework. So if anyone wants to help, it might finish at some point. So the future is a bit unclear, but the Beam is not dead. So go out there and build new amazing things on the Beam. You can embrace some of the new trends or just improve on the framework. Or a new, better language where you can actually express processes in a good way. If you can come up with that, it would be great. Or just keep on working and use Beam as your secret weapon. Thank you.
Okay. Do we have any questions? Just quickly check the app as well.
Ah, which one do you want? There's 3 more at least. We have signals, garbage collection, and memory. Garbage collection. Yes, that story is not that fun. So no, let's do garbage. Garbage collection. It's quick. We were parsing XML data, and for some reason we sent this data and it expanded. So suddenly one process needed more than 32 gigabytes of memory. No problem, because we had 2 terabytes in the machine. But there was actually a bug. No one had tried this before, 32 gig of memory in one process. So the garbage collector, there were some places where the pointer type in the C code was wrong, and everything crashed badly. But we fixed that, sent a patch to OTP, and they rewrote it, and nowadays everything works. Signals. Well, that one is also related to this. So, or it's related to sharing in the Beam. So it's very nice. You can create sharing structure. So if you have a tuple and you put it in another tuple, you still just use one tuple. And if you're working with XML, which for some reason you are, you can sometimes get these very complex trees that are not taking much space unless you send them as a message, because then it's expanded. And that is a problem. The last one. Okay, what was the last one? Signals, memory management, and schedulers. Yes. So one night when the system was really quiet and there was not like Black Friday or anything, And we had mostly all our customers in Europe, so there were like, at the night, nothing was happening. The system just died. And it took some time to figure out how this happened. But it turns out that Beam tries to be really, really nice and not use schedulers if they're not needed. So it will migrate processes to one scheduler. So if you don't have much work to do, in the end you end up with just one scheduler running. Now, if you parse XML, and you're getting it as a binary, and you need to do term to binary on this thingy. Term to binary at that time used 20 reductions, not just one, like some BIFs. So term to binary is a BIF, a piece of C code, using 20 reductions, even if it had to parse 4 GB of data. And it didn't stop either. It couldn't yield. There was no yield in BIFs at that time. So what happened was that you only had one scheduler, and then it said, oh, I had not much to do, so let me parse this binary. And I'm going to do it for a couple of minutes. And then Hart was like, hello, what are you doing? And there were no scheduler that could say, oh, I'm fine, because they were all sleeping. So then Hart said, well, I kill you then. And since we had 2 terabytes of memory, it took 1.5 hours for the system to restart. But we rewrote term to binary, made it yielding, and returning as many reductions as needed, and sent a patch to OTP, and they rewrote it. And now
Okay, great. Let's hear it for Erik Stenman. Thank you.